All right, this is question 10 from practice exam number 1 for physics 211. I'm going to go ahead and share a virtual whiteboard. I already have the pictures drawn because that'll save a lot of time. So what this question boils down to, once you filter out all the words, is that we're dealing with a person that's on a ferry, and the person is moving relative to the ferry, and the ferry is moving relative to the water. And in this case, relative to the water just means relative to some stationary point, right? Maybe a dock, what we would consider stationary. And so when it basically vector analysis is going to be our best tool here, because it gets really hard to start thinking about these sorts of problems. In one dimension, it's not so bad. You know, if you have a person walking on a train, so the velocity of the person with respect to the train, and you have the velocity of the train with respect to the ground, then to a stationary observer, they would see the person traveling at the velocity of the person with respect to the train plus the velocity of the train with respect to the ground. And there's a little hint here. So you'll notice velocity of the person with respect to the train, and then it's train with respect to the ground. So here's a little trick, is that if V sub PT plus V sub TG is actually going to equal V sub PG. So you see how the T's kind of connect each other, right? This one's subscript ends with T, and this one's begins with T. And so the T's kind of, don't think about it as actually mathematically combining, but this is just an indexing method for helping to understand these problems. So the T's connect these two velocities, and then the beginning of this first velocity is the person, and the second subscript of this velocity is the ground. So you'll notice that now we have the velocity of the person with respect to the ground, which makes sense because if this person is walking on the train in the same direction the train is traveling, and the train is traveling at some velocity in that same direction, somebody standing on the ground is going to see that person actually moving faster than the train. And in fact, the person on the ground is going to see the person moving with the velocity of the train plus the velocity of the person with respect to the train. So this is in one dimension. It's not so bad in one dimension. In two dimensions, it gets tricky. It's hard to visualize. It's not a static picture. And so vector analysis is our best tool. So in this case, we have this person walking on a ferry, and the velocity of the person with respect to that ferry is 1.5 meters per second north. Meanwhile, the velocity of the person with respect to the water, or with respect to a stationary point, is 4.5 meters per second at an angle 30 degrees west of north. All right, so once again, we're going to use this subscript thing, and we're going to go ahead and say that if the person's walking on the ferry and the ferry is moving, then wouldn't it make sense that the velocity of the ferry with respect to the ground plus the velocity of the person with respect to the ferry would equal the velocity of the person with respect to the water, or the stationary point? So if you're moving on an already moving object, then you get your velocity on that object plus the velocity that the object that you're on already has with respect to ground, or the water in this case. So using our little indexing again, we can make the statement that the velocity of the person with respect to the ferry plus the velocity of the ferry with respect to the water should equal, so these F's connect these two velocities, and then there's this person and this water subscript, and so this should equal the velocity of the person, oops, wrong color, the velocity of the person with respect to the water. Okay. So just try to wrap your head around this. Once you get it the first time, you won't really have to think much about it. You'll just be able to use vector analysis to forego the thinking process, right? It's an algorithm. So the velocity of the person with respect to the ferry plus the velocity of the ferry with respect to the stationary observer is equal to the velocity of the person with respect to that stationary observer. All right, so what do we know in this problem? We know the velocity of the person with respect to water. So we know velocity of person with respect to the water. We know velocity of person with respect to ferry. And our goal is to figure out the velocity of the ferry with respect to the water, or with respect to the stationary observer. So we're in 2 dimensions, so it's very important that we add these vectors like vectors, right, and not accidentally add them like scalars. And so let's first rearrange our vector equation to solve for the unknown. So the velocity of the ferry with respect to the water is going to equal the velocity of the person with respect to the water minus the velocity of the person with respect to the ferry. All right, so now that we're here, we can start figuring out, well, what is the vector of the person with respect to the water? Well, we're given an angle and we're given a magnitude. So you'll remember that we could essentially project the components, right? So this would be the westward component of the velocity of the person with respect to the water. And this would be the northward component of the velocity of the person with respect to the water. And so you'll notice that the northward component of the velocity of the person with respect to the water is adjacent to this 30 degrees. And so for adjacent, we'll use cosine. And so we'll take the magnitude times cosine of 30 degrees. And this is going to be in the north direction. So I'm going to indicate that with a unit vector that indicates that I'm in the northward direction. Then you'll notice that the westward component of the velocity of the person with respect to the water, and mind you, this is a right triangle, very important. This is opposite of the angle. And so we're going to use sine for that, 4.5 sine 30 degrees in the westward direction. And remember, this all stems from the idea that the sine of an angle of a right triangle is equal to the opposite side over the hypotenuse, and that the cosine of theta is the ratio of the adjacent over the hypotenuse. So if you're wondering where those come from, they come from these definitions of the ratios sine and cosine. All right, so there's our vector. I mean, we haven't taken the cosine and sine yet. That's the velocity of the person with respect to the water. That was the harder one. Now we've got the velocity of the person with respect to the ferry. And this one's pretty straightforward because the velocity of the person with respect to the ferry is straight northward. And so we've already got the magnitude. And so we could just say it's 1.5 in the north direction. And what the heck, let's add units. These are velocity vectors. So it's going to be in meters per second in this case. All right, now we can do the vector subtraction. First, what I'm going to do is I'm going to go ahead and do the cosine of 30. Should be 0.866 times 4.5. That leaves me with about 3.9 in the northward direction for this particular vector. And then sine 30 should be 0.5 times 4.5 is 2.25 in the westward direction. All right, so now we can combine these now that we have these in terms of real numbers. So we're looking for the velocity of the ferry with respect to the water. And we know that that's equal to the velocity of the person with respect to the water, which is a 3.9 north hat plus 2.25 west hat. And this is going to be minus our second vector, which is the velocity of the person with respect to the ferry. That's 1.5 north hat. So after combining like terms, 3.9 minus 1.5 gives me 2.4 meters per second in the northward direction, plus the 2.25 meters per second in the westward direction. So this is our answer of the velocity of the ferry with respect to the stationary observer or the water. The question, however, asks for the magnitude and the direction. So we're going to be taking this vector, right, which actually, now that we've solved for it, let's show what it represents. This is our answer. It represents basically, right, because of the velocity of the person with respect to the ferry plus the velocity of the ferry with respect to the water equals the velocity of the person with respect to the water, then these three vectors are related in a sum difference. This one plus that one equals this one. And so let's go ahead and notate that. This vector represents the velocity of the ferry with respect to the water. All right, last step. We know what to do when we have, so I'm going to draw this. I'm going to draw a right triangle to represent my new vector. And my new vector has it has a westward component of 2.25 meters per second and a northward component of 2.4 meters per second. So you can really measure the angle from wherever you like, but since we've already gotten our first angle measured from north, I'm just going to go ahead and measure our next angle from the northward direction. So this is the northward direction. And so to find the magnitude of this vector, right, that's going to be this length, or technically it's meters per second, but it's the magnitude is the length of the hypotenuse. So to find the magnitude of the velocity of the ferry with respect to the water, you could use this fancy symbol. The double vertical lines means find the magnitude, which just means to use Pythagorean theorem, Pythagoras' theorem, which is the root of the square and then sum the squares of each side length. Okay, and I already did this calculation just to double check before I made this video. It's 3.29. I recommend that you check it and let me know if I did something incorrectly. All right, so this is the magnitude, right? We're halfway done. Now we just need the direction. I'm gonna go ahead and round that 3.3 meters per second. Now remember, the direction when we're referring to a vector is going to be this angle and some reference, right? In our case, we're referencing north. So we could use, well, we could use sine, cosine, or tangent here, because now we know all the side lengths, right? This side length is 3.3. But just traditionally, we tend to say tan theta, especially when we have components, is equal to the opposite side. In our case, it's 2.25 over the adjacent side. Adjacent side in this case to the angle is 2.4. Okay, and I've already done this calculation, and it ends up giving you theta about 43.2 degrees, and we're measuring west of north. All right. So I'm trying to be as thorough as possible here, Hopefully I didn't ramble on for too long, and I hope that you find this to be useful, and I'll see you next video.